Toilet paper, a household item that we hopefully use to take care of business, sits right on the line of importance next to physics. Why? Because we use both toilet paper and physics every day. However true that may actually be, we need an understanding of both to answer the following question. A roll of toilet paper is dropped from the second floor of the school. Another one is dropped at the same time, but someone holds the end of the roll so that it unwinds as it falls. From what height should the unwinding roll be released from so that it hits the floor at the same time as the one dropped from the second floor? Now, before you jump straight into this question, you must at least have a sound understanding of these 5 physics concepts: centripetal force and acceleration, gravitational forces, rotational and tangential acceleration, torque, and moment of inertia, all of which are covered in this video. Starting with centripetal force and acceleration. Although it doesn't have anything directly to do with the toilet paper question, it still has some fundamental skills that you need to understand for AP Physics 1 and AP Physics C. Centripetal means center seeking and is often used to describe force and acceleration when an object is traveling in a circular path. Instead of a linear path like you would see in a kinematic question, an object is traveling in a circle, which is why it's important to know things like the circumference of a circle, which is 2 pi r, or pi times the diameter of the circle. If the object were to be released at any point in its circular path, it would have a tangential velocity. Velocity is usually described as displacement over time, but in this case, the displacement would be the circumference of the circular path the object is traveling in, and the time would be the period, or the amount of time it takes to make one revolution. Centripetal acceleration would be the rate at which the speed is changing when the object is traveling in its circular path. This acceleration vector would be pointing inside of the circular path and can be described as v squared over r, where v is the tangential velocity and r is the radius of the circle. Finally, you can derive an equation for centripetal force using Newton's second law equation: net force is equal to mass times acceleration. You can sub in acceleration for centripetal acceleration, which is v squared over r, and multiply it by mass to get the equation for centripetal force equal to mass times velocity squared over r. Many examples of centripetal force and acceleration exist, such as Ferris wheels, satellites, and planet orbits, which you get much more into detail when exploring Kepler's laws. Gravitational forces are defined as forces of attraction between two objects. The force of attraction between them can be described by the formula Fg is equal to big G times mass 1 and mass 2 divided by r squared, where G is the universal gravitational constant, mass 1 is usually the larger mass, and r is the distance between the two masses. If you use this formula on a person with respect to the Earth, you can plug in your knowns, such as m1 being the mass of the Earth and r being the radius of the Earth. You will then get the mass of the person times 9.81, which is a known number in physics as it represents little g, or the constant used to describe the acceleration due to gravity. This then gives you the more common formula, which is force of gravity, or Fg, is equal to m times g, which is also known as the weight force. This force is extremely important because it is what causes both toilet paper rolls in the experiment to fall when they are released.
Now we have rotational and tangential acceleration, and they deal with the change in radians with respect to an axis, as well as rotation of objects usually due to torque. And you can see here that tangential velocity, or v, is related to angular velocity, omega, by the equation v equals omega times r, seen on the bottom of the screen. Additionally, tangential acceleration, or a, deals with the rate at which an object's velocity changes along a straight path. It's related to rotational acceleration by the equation a equals alpha, rotational acceleration, times r, which is the distance from the axis of rotation. This also means that tangential acceleration is directly proportional to rotational acceleration. Lastly, you can also see that omega, or angular velocity, is equal to the change of theta over time, and alpha, or angular acceleration, is equal to the change of angular velocity over time. Have you ever wondered what makes objects rotate? What causes a door to swing open, or maybe a wrench to tighten a bolt? The answer is actually a fundamental concept where we have here and it is torque. Now let's start by defining torque and understanding the equation behind it. As you can see, torque is directly related to the distance from axis of rotation, assuming force is constant, as torque is mathematically expressed as T equals F times R times sine theta, where T is the torque, F is the applied force, and R is the distance from the axis of rotation, also known as the lever arm. And theta is the angle between the direction of the applied force and the lever arm. That being said, knowing how torque works, it also has a connection to rotational motion. When an object rotates, in this case being our unrolled toilet paper, its rotational acceleration is influenced by the net torque being applied. And as you can see here, mathematically the equation would be T net torque equals I times alpha, I being the moment of inertia and alpha being the angular acceleration.
The last concept is moment of inertia, which is described as the measure of an object's resistance to rotational motion about a given axis. It's represented by the letter I, and when talking about discrete point masses, such as the example below, the moment of inertia is equal to the sum of the masses times their distance from the axis of rotation squared. However, when talking about continuous masses, the moment of inertia takes on a different form, which is the integral of r squared with respect to dm, where r either represents the radius of the given mass or the length. When talking about moment of inertia, there's also the parallel axis theorem, which is a theorem that states that you can find the moment of inertia of a rigid body on an axis parallel to its center of mass axis using the formula the moment of inertia around the center of mass plus the total mass of the system times the distance between the center of mass axis and the parallel axis squared. Now that we have the concepts down, we can move on to the calculations needed to answer this question. Since the grading rubric states that this video should be tailored toward AP Physics 1 students, there will be a visual aid located on the screen while we do the necessary calculations. The first step is to set up a Newton's second law equation, where the net force for the dropped toilet paper is mg and the net force for the unrolling toilet paper is the difference between tension and the weight force. If you set mg equal to ma, you can cancel out the masses and you're left with g is equal to a. However, for the unrolling toilet paper, we realize that the net force isn't just mg, and that means that the acceleration isn't g. To solve for both accelerations, we use the equation delta y, or height, is equal to 1/2 at squared. We know that the acceleration for the dropped roll is equal to g, so we can sub that in. However, this isn't the case for the unrolling toilet paper, which is why we just leave it as a. We then solve both equations for time, by multiplying each side by 2, dividing by a, and taking the square root of the variables. We repeat the same process for the dropped roll, except we are dividing by g and not a. We know from the question that both rolls hit the ground at the same time, so we can set both equations equal to each other, and solve for the height at which the unwinding toilet paper should be dropped. We do this by squaring both sides of the equation, dividing by 2, and multiplying by a, to get the height at which the unrolled toilet paper is equal to the height of the dropped toilet paper divided by g and multiplied by a. The next step is not necessary for AP Physics 1 students because it uses everybody's favorite subject, calculus. For this diagram, you can also see that there are multiple labeled parts. R1 is the radius for the smaller cylinder, while R2 is the radius for the entire paper roll. Instead of using h for height, we will be using L. To start off, we take the derivative of the volume equation for a cylinder, which is pi r squared L. This gives us dV is equal to 2r pi L dr. Next, we're going to take our density equation, where density is equal to mass over volume, and we're going to rearrange it to solve for mass. This gives us m is equal to dV, and we're going to take the derivative of this, which is going to give us dm is equal to d dV. If you notice, dV is the derivative of volume, which is what we solved for earlier. We can sub this in for our dm equation, which is going to give us dm is equal to d times 2 pi RL dr. With what we have now, we can plug it into our moment of inertia formula, which is the integral of r squared with respect to dm. If you sub in dm, you get the moment of inertia is equal to the integral of r squared times d times 2 pi RL dr. To properly evaluate this integral, we're going to set its limits to r1 and r2, with r1 being the lower limit and r2 being the upper. We then factor out the integral's constants, which are 2, pi, density, and length, or height. On the inside of the integral, we're left with r squared times r, which is just r cubed. The integral of r cubed is r to the 4th power over 4, and we're going to evaluate this from r1 to r2, with 2 pi dl unchanged because they are constants. To evaluate the function, we're going to put it to where the function's value at r2 is subtracted by the function's value at r1. You can bring out the 1/4 as a constant, leaving the outside to be pi dl over 2 times r2 to the 4th power minus r1 to the 4th power. Using algebra, you'll notice that r2 to the 4th power minus r1 to the 4th power is a difference of squares. You can then break up the entire equation to give you 1/2 pi dl times r2 squared minus r1 squared times r2 squared plus r1 squared. With this large equation, we can simplify it. We do this by finding the formula for the volume of a hollow cylinder, which is the volume of the larger cylinder minus the volume of the smaller cylinder. You can factor out pi and L, which gives you volume is equal to pi L times r2 squared minus r1 squared. We can simplify this further by referring back to our density equation that we rearranged, where mass is equal to density times volume. Plugging in volume for what we just solved for, you would get mass is equal to pi dl times r2 squared minus r1 squared. We can finally sub in this equation for what we had in our moment of inertia equation. And when we do, we're left with the moment of inertia of a hollow cylinder is equal to 1/2 times the mass times r2 squared plus r1 squared. With these oodles and oodles of information, we can finally solve the height at which we need to drop the unwinding roll of toilet paper so that it lands at the same time as the one just being dropped. We start with the equation net torque is equal to moment of inertia times angular acceleration. However, the moment of inertia in this equation is the moment of inertia around the parallel axis, which we can find using the equation above. We already know the moment of inertia around the center of mass, so we just need to add that to the mass of the toilet paper roll times the distance from the parallel axis to the axis of center of mass, which is just r2. From here, we can distribute the 1/2 m into the parentheses and add like terms to get 3/2 mr2 squared plus 1/2 mr1 squared. We could then factor the 1/2 m back out again to get 1/2 m times r1 squared plus 3r2 squared. Now that we have this equation, we can refer back to the net torque equation. We know that torque can simply be put as force times radius, and we know from the diagram that the force is the weight force, mg, and the radius is r2. To solve for angular acceleration, we can divide net torque by moment of inertia, which, if you cancel out in rearranged terms, gives you angular acceleration is equal to 2g_r2 over r1 squared plus 3r2 squared. We can bring back our old equation of h drop over g times a, and we know that angular acceleration times the radius it acts on is equal to translational acceleration. With alpha being what we just solved for and r being r2, our translational acceleration ends up being 2g_r2 squared over r1 squared plus 3r2 squared. We can then plug in this acceleration into our equation, and with the g's canceling out, the height at which we must drop the unrolling toilet paper is equal to 2h drop r2 squared over r1 squared plus 3r2 squared. After all these calculations, the final step is to experimentally test them. I managed to grab a hold of 2 guinea pigs located at my area of residence in order to prove that my calculations were indeed correct. The toilet paper roll that wouldn't unwind was set 3 meters above the ground. The unwinding roll, however, was located only 2 meters above the ground. With the setup done, all I had to do was give the guinea pigs the signal, and they would release both toilet paper rolls at the same time. With the experiment happening right in front of my eyes, I clutched my chest. Judging from the audio and video, it's safe to say that both toilet paper rolls hit the ground at relatively the same time, and the math still provided a very accurate prediction on where I should hold the unwinding toilet paper. With the results giving us a clarity of mind, I can sleep peacefully knowing I won't have to write a lab report.